Hi guys, today we are going to solve this problem here, which is asking what value resistor should this load be in order to allow 14 milliamps of current to flow through it. So you can see that this resistor here is connected to this, moderately complex circuit here. And so we want to figure out what value this thing would have to be in order for 14 milliamps to be flowing through that resistor right there. And so the way that I'm going to approach this is this. So we know that when we find the Thevenin equivalent of a circuit, it looks like this. So we can basically reduce the complexity of any circuit and turn it into this model right here. We have to do that from the perspective of some component. So I'm going to choose this load resistor here. That's the component that I'm focused on. So I'm going to remove it from the circuit. And so my circuit is now going to look like this. Sorry, this is just taking me a second to draw it. Okay, so there's the circuit. You can see right here is where that resistor was. So I'm just going to remove this load resistor from the circuit. And I'm saying that once I do that, I can take this circuit right here and I can reduce it to a model that looks just like that. So let me first label these. So this is 12 volts right here. This is 100 ohms, 25 ohms, 50 ohms, and 75 ohms. So when we're finding the Thevenin equivalent of something, the first thing that we need to do is remove the load. We've done that. The second thing that I need to do is I need to find VAB. That is the difference between the voltage here and here. And that becomes V Thevenin. So I'll write that. VAB equals V Thevenin. All right. So I guess in this case here, I've got a little bit of resistor reduction to do. Because you can see I don't actually know any of the voltages in this circuit except for across the supply right here. So there's going to be a drop across this resistor because the current's going to flow like that. There'll be a drop. I'm going to call this VA right there. And then that's also VA. So there's going to be between VA and ground here, you can see there's 3 drops right there because we don't know what VA is yet, but I know that this node right here is VA. And I know this node right here is 0 volts. So you can see we've got a 3-way divider right here. Well, I just want to know what is the voltage drop across the 50 ohm resistor right there. So I guess the first thing I ought to do is find RT for this circuit. And then once I have RT, I can find IT. Once I have IT, I will know the drop across this 200 ohm resistor right here. So let's reduce these resistors. So we've got 75 plus 50. Okay, so that's 125. Plus 25 is 150 ohms. And it's in parallel with 100 ohms. Okay, so this and this will all reduce to one resistor. And that's all in series with 200 ohms. Okay, so we've got 150 in parallel with 100. So we're going to do the product over sum rule here. It's 150 times 100 divided by 150 plus 100 equals whatever the equivalent of these two in parallel is. So let me do that. Give me just a moment. 150 times 100 divided by 250 is 60 ohms. And that makes sense. You should never get an answer that's larger than either of these resistors, and your answer should always be smaller than the smallest resistor, which in this case is the 100. So anyway, this becomes 60 right here, and we're adding 200 to it. So RT equals 260 ohms. Well, there's 12 volts across 260 ohms. And so we know the total current in this circuit must be 12 divided by 260. And that looks like 46.15 milliamps. 46.15 milliamps. Okay. So that's how much current is going through this 200 ohm resistor right there. So let's see what the drop across that is. So 46.15 milliamps times 200 ohms. That is a drop of 9.23 volts from there to there. So if we start at 12 right here and we drop by 9.23, that means that VA is 2.76 volts. Okay. So we know that there's 2.76 volts right there, 0 volts right there. This is just a 3 resistor voltage divider. I want to know the voltage across the 50. And so that's going to be the difference in voltage between here and here. So that's the voltage being divided. So that's 2.76 volts. And we are multiplying that by, this is the one that we are looking for the voltage across. And the total of this whole divider is 75 plus 50 plus 25. So that is 150. And let's see what the voltage is across the 50 ohm. 2.76 times 50 divided by 150. I made a mistake. Let's see here. Oh, I put 27.6. Oops. 2.76 times 50 divided by 150. Now we'll get it. So it's 920 milliamps. Oh, millivolts, I'm sorry. I am screwing up left and right here, and I'm not going to do this over. So V Thevenin is 920 millivolts. All right, well, let's see what R Thevenin is. Well, before we can find R Thevenin, that is the resistance measured between A and B, we need to turn this circuit off. So how do you turn a voltage source off? Well, to turn off a voltage source, you short it. To turn off a current source, you open it. So I'm shorting this voltage source now. Okay, so I am breaking down towards points A and B. So let's reduce towards the spot that we're breaking down towards. So it's 200 ohms in parallel with 100 ohms. So that's going to be 66.66 ohms right there. Okay, so now our circuit's going to look like this. 66.66 ohms. Here's the 25. Here's the 50. Here's the 75. This is the spot where the voltage source was. So this is 50, 25, 75. And here's point A. Here's point B. All right. So it's very tempting to say that everything is in series here, but remember, point A is this node, and point B is this node. So actually, this, and this are all in series, and those are all in parallel with the 50 ohms. So RAB, that is the resistance read between this point and this point, if you put a meter there like this, it's going to be 50 ohms in parallel with 25 plus 75 plus 66 point, and I can't fit it, but that's supposed to be 66.66 right there. So let me do that math so I can clean that up a little. 25 plus 75 plus 66.66 is 166.66. So RAB is 50 ohms in parallel with 166.66. So let me figure out what that is. I'm going to do product over sum. So 50 times 166.66 divided by 50 plus 166.66. So it's 38.46 ohms. There it is. So our Thevenin is 38.46 ohms. Okay, well, back to the original question. I'm sorry that this took so long to get to that point, but remember, we removed that load resistor at the beginning of the problem, and we reduced this whole network here to this. Well, now it's time to put the load resistor back into the circuit. So here it is. And they want to know what its value should be, RL here, what its value should be to allow 14 milliamps of current to flow through it. So that's actually a pretty easy problem at that point, because we know that there's only one current in this entire circuit, that is IT, which is flowing around this loop like that. So the formula for IT is V Thevenin, that's this voltage, divided by R Thevenin plus R load, right? Because RT in this circuit is just these two. So it's going to be 0.92 volts divided by 38.46 plus our unknown resistor, and that equals 14 milliamps. All right, so we've just got an algebra problem now. So here's what I'm going to do. I am going to multiply both sides by this right here. And so it's going to look like this. I don't have much room to write it. Come on. 0.92 volts is equal to 38.46 plus RL times 0.014. So I've got to use the distributive property there. And let's see what we get. So 38.46 times 0.014 is 0.538. And it's going to be plus 0.014 RL. That all equals 0.92. All right, so let's subtract 0.538 from both sides. 0.92 minus 0.538 is 0.382. and that equals 0.014 RL. And we're going to divide both sides by 0.014. And we get 27.28 ohms for RL. So 0.382 divided by 0.014 equals RL. So there we have it. We know what RL should be.